Okay, I'll give maybe a couple of minutes more. We'll start in 3 minutes. Three. Yeah. Okay. Sure. Yeah. 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 Okay. While we are waiting, are there any questions from the previous class? You can put your hand up in Zoom, or you can use the chat button, chat window if you want.
Were the questions from your last lecture already answered?
Last lecture, there are a lot of questions. I answered them. Okay, let me check. There are many questions yesterday. Uh,
I see a couple of questions there. If you want, you can respond to them.
so one of them actually has nothing to do. I think I yesterday said with gravitational waves. It is about whether I think magnetic fields can heat up the accretion disk. That question, I'm sure somebody will give a relevant lecture, and you can ask. And then if then there is a question that if we see the image of the black hole, we see the light on the edges of the circle, but not at the center because, well, nothing is coming out of the black hole. What you are seeing is the lensed background, and that not just the background, the accretion disk can also be lensed. So you basically get a distorted picture. This is again nothing to do with gravitational waves, but you can look up. Let's say how you can. I think that there will be explanatory documents for the Event Horizon Telescope images. Okay, there is one question that if possible, what would be the a way to detect gravitons? I think first thing would be to predict gravitons, which would be which would require a quantum theory of gravity. uh, I don't know how whether it is not even clear whether gravitation is quantized or not, and if it is, then probably there will be gravitons predicted by different theories. Okay, so far we are. I think I explained this yesterday also that we are essentially focusing on the classical gravitational waves. Okay, we will start now. So yesterday's lecture was about the origin of gravitational waves, like how the gravitational waves are predicted by Einstein's theory of general relativity, and then there was some we discussed about some sources which can astrophysical sources that can emit gravitational waves. Today's lecture will be on essentially on different detectors and detection of gravitational waves. The the first detection of gravitational waves happened long time ago. Uh, this was through the observation of a binary pulsar, which was done by Hulse and Taylor. They observed this binary. So what happens is that when gravitational waves are emitted, I think I told you yesterday that to compensate for the loss of energy, a binary comes a bit closer, and then its period changes. So essentially, when that happens, the period no longer closes exactly. It slightly starts precessing. Now, basically these periastrons start moving. I mean, so this will be like ellipse like this and things like that. And these things can be measured very well. And this was done by Hudson Taylor, and that the binary itself was observed for uh, more than 30 years. And you see the measurements which were here, that these black dots with error bars show the measurement, and then this solid line is basically fitting general relativity prediction, and that matches so well that this was a real confirmation, big confirmation that gravitational waves exist. But then it was an indirect detection because we did not really detect gravitational waves. What we detected is what happens if a system emits gravitational waves. That is, it loses energy in a certain way, uh, and that was matched. To see how to detect gravitational waves directly, we need to first see what happens when gravitational waves fall on matter, how it interacts with matter. So this is let's say there is a ring of particles like this, and the plus polarization of gravitational waves is incident on the plane, that is on, let's say, on the screen on which you are seeing. So it is incident on in that direction. Then this ellipse, this circle would get deformed in this way. It will become ellipse, basically uh, elongated and compressed kind of, I mean, elongated in different directions, you can say. So this kind of ellipse. Okay, I'll play these things. So something like this is what is going to happen. Okay, to the when gravitational waves are falling on this on a ring of particles. Similarly, if instead of plus polarization, it is the cross polarization, then basically in the same coordinates, then this ellipse gets rotated by 45 degrees. And that is what we mean by when we say that, gravitational waves are polarizations are at 45 degree. In other words, if you unlike electromagnetic waves, where if you put a 90-degree rotation, one polarization direction becomes another one. Here, if you rotate the coordinates by 45 degrees, one polarization becomes the other polarization. That's plus becomes cross if you rotate by 45 degrees. But then this rotation has to be done through a basically a matrix transformation. In case of electromagnetic waves, it is a vector which gets transformed. Here it's a matrix or a tensor. Okay, so then there are some calculations. If you have done a course on, okay, you have learned some little bit of general relativity in this course. So what happens here is that suppose you consider a light propagating along the x-axis, then for light this ds square is 0. So you can then get this equation, ds square is c square dt square minus uh, basically plus g mu nu, well, the rest of the components, basically g I j is dx I square, if you remember what you learned in the general relativity course. But if you are going along the x-axis, then y z components are all 0, and you end up getting an equation like this, where this xx component is basically the metric perturbations here, meaning the whole thing is gxx. But hxx, this gravitational waves contribution, the perturbation due to gravitational waves is very small. So you can then write this equation in this form, basically take a square root on both sides and integrate. Then you get this term, which can be approximated as 1 minus, hxx by 2. And hx, we are here considering only the plus polarization, so you can put it h plus by 2. And then if you consider that the gravitational waves frequency is small, that is, it is varying slowly, then you can basically take it as constant. It comes out of the of this integral, and meaning there are two parts of the integral. From the second part, the first part is what would have happened without the light travel time, without any gravitational waves, and this term tells you how much is the contribution because of gravitational waves. So this comes out to be basically some h plus by 2 into dx. Then if you put this as the delta L, meaning that the difference Tx minus Tx without gravitational waves, then this would be the change you see in the arm length divided by the arm length if you do, because you will end up getting an L here because this is a constant. So when you integrate this dx, you will get an L. Put that here, and then you get basically this quantity 2h plus, and that is here we are also taking into account that the waves are in opposite phase along the x and the y axis. So that gives you a factor of 2. Basically, we are taking ty minus tx. That is, this delta L is the difference between delta L along y axis and x axis. Anyway, so this is, I mean, you can do all these things later on. The main thing to understand is that when gravitational wave would fall on a ring of particles, it will do this kind of motion. Now, it does not have to be a ring. It could be just a rod like this along the x-axis. Then also it would try to fluctuate like this. But then there are elastic forces which would try to keep it in the same place. Nevertheless, it can still create some kind of vibrations in the rod, if especially where there is near the resonant frequencies of the rod. But then you could also put a Michelson interferometer like this, where there is one mirror here and one mirror there on this ring of particles, like meaning there is no ring of particles that way. It is just a imaginary ring, and you put these two, and these are called the test masses. And there is a beam splitter, and if you put a laser beam which divides in two parts, and then if you collect it here, I'll show you a proper video of that, then you can detect gravitational. We'll come to that in a moment. The first attempt to detect gravitational waves happened in 1970s or 60s by Joe Weber in Maryland. Even though he could not detect the gravitational waves, he is considered the father of gravitational wave astronomy because of his effort, and which eventually led to the detection that we have. So this was a bar detector that he proposed, where the resonant bar detectors, that is when gravitational waves pass through it, if there is an overlap with the resonant frequency, the bar will vibrate, and then there are all the different sensors here which would measure the vibrations without perturbing the bar, and that is a very challenging thing. So eventually, this did not attain enough sensitivity to really detect gravitational waves, even though there were some false claims. But these detectors are relatively easier to build, even though not sensitive enough, and cheaper also. There were a lot of research later on to cryogenically cool these parts, because the Brownian motion at room temperature can be more than the perturbations that are produced by gravitational waves. So then the bar itself cannot see every direction. That is, gravitational waves coming from only certain directions, it will be able to respond. Which is why people also tried to do kind of omnidirectional antenna, where it can receive gravitational waves from all the directions, and so on. But anyway, so far there has been no the sensitivity is not adequate, which would be necessary to detect gravitational waves, astrophysical gravitational waves. Of course, if something happens in our own galaxy, let's say there is a supernova in our own galaxy and it is asymmetric enough, these detectors may be able to detect something, but the probability of that is pretty low. Okay, moving on to the interferometric detector. So here is the schematic. So you can see that there is a laser beam which came out. Okay, let me play it from the beginning so that you can focus again. So you see what happens is that a laser beam comes out of here. There's a beam splitter which splits the beam in two parts, and then these are the two end mirrors. And this is what is going to happen when gravitational waves come. So now you can see from the beginning. So this laser beam is divided. It hits the end mirror, and another one comes here. Then they are combined in the photodetector. When they are in a normal case, they are in exactly in the opposite phase. So the amplitude will be 0. But when gravitational waves come, these things start moving, so the amplitude will change. And that is the basic idea of gravitational wave detection, even though the interferometer is far more complicated, which we will see very soon. So this is the idea. So any questions here? Okay. Then, so there are right now 5 interferometric detectors which are large enough. That is, let's say, few hundred meters to few kilometers long. 2 in the United States, in Hanford and Livingston. They were almost diagonally opposite here, like in 2 locations which are very far away as possible in a country, and that is because uh, the disturbances, the common disturbances they face, that let's say seismic disturbances, could be minimized this way. And also, if these are far away, then using uh, cross correlation between these 2 detectors, like what one does in radio astronomy, one could map the sky, and also this will also give you a better sky resolution. That is, where the event has happened, you will know somewhat better if there are 2 detectors. I mean, of course, with 1 detector you cannot say anything. With 2 detectors, you can at least locate them on a ring on the sky, and then along with their response functions, etc., you can reasonably reduce the area. For proper localization, you need 3 detectors, which we will see later. Now, then there is a detector called GEO. Acha, there is the Virgo detector in Italy. This is a 3-kilometer detector again, similar to the LIGO detectors, though the sensitivity is still quite low compared to these 2. There is a detector in Germany which is called GEO 600 meters. This detector, even though is not even much less sensitive, a lot of activities for technology development happens here. Then there is a Kavla detector which has come up recently. This is again a 3-kilometer detector, but underground, and this is cryogenically cooled to get higher, to reduce thermal noise and so on. And this is the design for the proposed plan for the LIGO India detector, which we hope will come online soon. Okay, there are some questions. So let me answer them. The gravitational waves are strong enough to shift the mirrors. The mirrors get shifted by like about 10 to the minus 18 meters. That is the effective, which is smaller than the size of a proton. So even though the mirrors are kept extremely free, meaning they're in vacuum, hanging from strings and so on. So that is the small disturbance that happens, and we are able to measure that. Mm. How do we isolate this effect from the terrestrial perturbations? Well, that will come the later part of the talk. Okay. Other question is that does the gravitational wave only stretch the space? Wouldn't it also stretch the wavelength of the light or laser used and cancel the changes in interference pattern? This is a very common question, and there is an answer, which is there is a document, or actually a American Journal of Physics article by Peter Solson, which explains this, that why that does not happen. If you are interested, you can look it up. Okay, there is a question that how many kilometers? It is the proposed length is 4 kilometers. Okay, moving on. This is the picture of the LIGO Hanford detector. This is 4 kilometers long, and 4 kilometers is pretty long, meaning if you compare a city, this could be like half the length of a city. And so this is basically, there is a cover on this, which protective cover. This is like a kind of like concrete cover, and then the beam tube goes inside, and the end mirror is here. The beam splitter is here somewhere inside. This is the main building. Okay. Now, okay, so even with this long detector, this 4 kilometer detector, it is not enough to get the, it's not optimal to detect gravitational waves. You need much bigger detector because you are trying to detect about 3000 kilometer uh, wavelength. Okay, so there are still questions. Let me see. How can we differentiate the disturbance of perturbation caused by gravitational and natural? I think I answered this yesterday, but we will see. You will see there are different methods which are used for that. Why they are 4 kilometer long? So the requirement for to detect gravitational waves is that, I mean, you if you want a detector which is sensitive enough, because if your detector is not sensitive enough, then you would be wasting a lot of money. When your detector is the most sensitive for a specific detection, then that is the best use of the money. But even then, and of course, science is certainly limited by money. The best use, even in that best scenario, the signal is still quite weak compared to noise. Now, since you are trying to detect 3000 kilometer wavelength, the optimal wavelength, the size of the detector, the arm length, is basically lambda by 4, which is 750 kilometers. But the problem is that 700 kilometer length on the Earth is very difficult to get. I think if you know, the Earth's radius is 6,400 kilometers. It's a very long distance. However, you can reduce it in this way, that you could either fold the arms so that effectively you can get longer arm length, but then this becomes quite challenging because there are multiple reflections, and then each one of them will cause losses, scattering, etc. And mirror, every reflection is a problem. So this would be one of the big challenges. Rather, what is used is a Fabry-Perot cavity. So in each of the arm, another mirror is put like this, so that light enters this cavity and then bounces back and forth on the average 300 times or so. So then effectively your length of this detector becomes of the order of 1000 kilometers, or at least few hundred kilometers. And that is how the arm length is increased. Now, if you try to increase this even further, then this is not going to work. And there are reasons behind it, that why you cannot arbitrarily increase this, because then some other noise, which is called the radiation pressure noise, would become much stronger. Okay, so there are more questions. Okay, one question is that how does earthquake affect the reading of the device? Yes, it does. So, but then earthquakes are not so frequent. So, I mean, we detect a signal, let's say once a week, which would be like 1 second long. The probability that an earthquake was happening exactly at that time is very low. Then the question is that since the arms are so long, how do we account for the change in altitude of the land? Well, I mean, that is not a big problem, because you can always dig, meaning this is light travel time, right? I mean, light travel path, so it has to be straight. So if there is a hill, then you just draw a small tunnel and things like that. I mean, and you choose a land which is reasonably flat, not exactly, but like reasonably flat. You can so wherever it is going down, you can make small bridge, or whenever it is too high, you can dig it through and things like that. Okay. Then there is a question is that the distance moved by the mirrors is very small, of the order of 10 to the power minus 18. Is it possible for visible wavelength to detect it? What do you mean by that? Meaning, the distance change is very small. That's about it. And then you can, and we are using this laser light which is being sent is actually infrared, but could be visible also. But then visible has some design challenges, which is why it is chosen as infrared. But this has nothing to do with the gravitational frequency. Okay, what is the need to have kilometers long arm to LIGO detectors? Does the phase difference between the interference depend on the it is basically that light. Okay, I think I showed this diagram picture. The strength signal, the signal that you detect in this interferometer is proportional to is basically the ratio of the length change by the length. So that is why it is called a strain signal. So what you are detecting is this delta L. So if L is large, delta is also large for the same signal, which is why you want to make the detector as large as possible. But that is not the only thing. The thing is that if the wavelength is so large that to optimize the detector performance, you need a detector which is large. Like for radio antennas are much larger than optical telescopes. It is kind of like that. Um, okay, next question is that in the later case, we will also have the loss at reflection. Yes, that is there, but reflection losses are there, but then you see you are making a small mirror here. Here the mirror would be much larger. So the loss, even I mean you have to. So the challenge is that you have to make kind of very good coating for this. If you have such a big mirror, yeah. So one thing is that you could reduce the quality of the coating in this way. Here it will be more, but if you reduce the quality, then I guess it will become a very big problem to align the mirrors properly. So it is not that it is not going to be that straightforward, and this is going to be much bigger than this because you want hundreds of reflections like this, not just 4 5. So those things will become very challenging. Okay, there are two more questions. Let's see. Uh, apart from theoretical predictions, are there any of our measurements proving that gravitational waves travels with the speed of light? Yeah, I will show that. Uh, well, there is no proof. You can only disprove it. That if you detect a deviation, then you know that this is not correct. And all you can prove is that it is consistent. Okay, I'll come to that. Whether it will be possible to make arrangements like array of interferometers to detect gravitational waves effectively. Yeah, that is what actually is being done. The detectors I showed form a network of detectors, these three, and they together detect at this point. And that also helps us to localize the source. I'll show that in a moment. Okay, now let us move on. So this is the schematic diagram of the advanced LIGO detector, which has detected gravitational waves. So this laser comes through some initial mode cleaners and so on. You want a kind of a perfect Gaussian beam, so then it enters this cavity. Okay, let us start from this part. So this I already explained that this is a Michelson interferometer with fabric pair arms. So that improves the so that kind of brings the interferometer to the optimal length of, let's say, a few hundred kilometers. It could be 500 to 1000 kilometers. Then the next thing is that, but the sensitivity is still not enough. In order to get enough sensitivity, you need very large amount of power, which turns out to be about 750 kilowatt. So how do you get this much power? So what is done is that there is another mirror which is put. It's called the power recycling mirror. That again pushes back all the light that was coming here to inside this. So it also acts like a fabric cavity. Like light is like trapped here. More the light, less the short noise, and that's how this is designed. So this is quite complicated, but the basic idea is not so complicated. And these are the some of the specifications. You can see, let's say the length is like this, nearly 4 kilometer. The finesse, which is called, which is basically the effectively determines how many times the photon is going to bounce inside this cavity, is like this. I mean, all these parameters. The important thing here is that all these parameters are kind of flexible in the sense that this has been designed for this detector, but then there is no reason to believe that this is the only possible way, the best configuration. One could improve the design and then get better and better designs. Now, one of the things to notice is that the mirrors which are hanging are very heavy, 40 kilo. So you may think that why 40 kilo? Because gravity may not be able to, gravitational waves may not be able to move it. But the thing is that, as you know from Galileo's experiment, effect of gravitation is independent of the mass. So the effect of gravitational waves on 40 kg mirror and 1 kg mirror would be the same. But when the mirror is heavy, the other forces have lesser effect on the mirror. And that is why you want to make the mirror as heavy as possible. So that the radiation pressure that I said, that when this laser is falling on the mirror, is creating small fluctuations because of the fluctuation in the radiation pressure, because of the photon counting error. Those things can be much reduced if the mirror is heavy. But if you make it too heavy, then the strings, which also have to be of very good quality so that they don't create any noise, may not be able to sustain them. So this is how things are optimized. So at the end of the day, here is this is the design sort of goal for this detector. So what is plotted here is the noise level expected from different kind of sources. This is frequency and this is noise converted in equivalent strain. That is, that what is the minimum strength of gravitational waves required in a given frequency band in order for this detector to detect it. So lower the curve, better it is. The lowest frequencies are dominated by seismic noise. Okay, so this is the seismic noise part. The highest frequencies are determined by photon shot noise. This is the same noise which you see when you try to take, let's say, picture with a digital camera or a mobile phone at night. The picture either gets pretty noisy or it gets blurry because your camera is trying to integrate for a longer time to accumulate more photons. So basically, that photon counting noise appears here. Higher the laser power, lower it is, and better the seismic isolation, which I'll show in a moment. Better this lower this noise. The central parts, these parts are dominated by thermal noise. That is the motion of different molecules due to basically because of their own temperature, like fluctuations in the strings, the mirrors, everything is moving, right? Everything has some half kT energy per degrees of freedom that can create enough noise. So this is the basic noise diagram. And these are, now I'll show you some of the pictures of the detector. So this is the kind of the schematic diagram. These are the vacuum tubes. This is the beam splitter. These are two mirrors, like which are called the basically these are the inner side mirrors, and these are the end mirrors. Okay. Then, so this is how they look actually. Even though in this picture this may look very small and narrow, they are pretty big, and you can see that compared to people standing here. Sort of these are the kind of chambers from in which those optics etc. are stored. This is the suspension. Somebody was asking that how we prevent the mirrors from getting perturbed by the seismic vibrations. So the mirrors are, first there are seismic stacks. So there are different kind of isolation system. Like you put some springs on the ground, then may create a platform, and from there you hang this through some pendulums. Now, what happens in a pendulum is that even though if you take a pendulum, you imagine that you are holding like a stone and tied with a rope, and you start moving it, okay, slowly. You will see that it is kind of that stone is moving along with your hand. But if you try to move your hand extremely rapidly, you will see that actually the stone is not moving much. Your hand is moving much more. So that is basically what it means is that at high frequency, the a pendulum acts as a low pass filter. That is, it shields, it does not allow the higher frequencies to pass. So what happens is that if you create this cascaded kind of pendulums, so 4 pendulums are there, then each stage blocks some of those high frequency seismic noise. Our target is to have very good sensitivity at around 100 hertz. And seismic oscillation, so if in each of these pendulum actually have this resonance frequency of around 1 hertz. So with 4 stages of pendulum, the seismic noise above few hertz becomes very low, and that is how the seismic noise is prevented. This is the laser. To increase the laser powers, basically to reduce short noise, a very high quality laser is used. The laser pointers that those are which are used in a lecture, typically 1 milliwatt. You could have maybe a 5 milliwatt laser. The advanced LIGO laser is capable of is actually operated at 70 watt power, which is way more than, as you can imagine, milliwatt. I think it will be what, maybe at least 1,000 times, maybe 2,000 times more powerful, and which is why it needs an elaborate setup. And also it's a continuous laser, and it has to be the beam shape has to be very good, and so on. It has to be very good quality. Frequency has to be very stable, and things like that. And these are the kind of optics which are used for different purposes. Anyway, these are just some pictures I wanted to show. So this is the real noise in the detectors. Okay, as you can see, they look very different from the theoretical smooth curves. And this is the main challenge, that even though you can propose a detector of this kind of very high sensitivity, the actual noise that you get when you run it, it looks very different, and it is very challenging to reduce this noise. It takes years to bring the noise down from here to here and things like that. And several PhDs have to be used. This is the Virgo detector. These are the 2 advanced LIGO detectors. Advanced LIGO was here at some point, and as I said, it took years to bring it down to this level. Now, because the detectors are noisy, you have to use sophisticated data analysis technique in order to detect those signals. So what is used, and which was kind of Indian researchers, especially at IUCAA, played a significant role in developing this. This method is called the match filtering. So what is done here is that basically you use the knowledge of the signal to detect the signal. I think it is better with this picture. So if you see, okay, there is a question before we move to that. When such a 2000 powerful laser is used, will it not melt the mirror used as a build? Okay, so there are care is taken so that it does not only melt, but it does not deform. So the optics has to be chosen in that way. So what happens is that even though the mirror would not melt, of course you choose the material that way, it could deform, and those deformations could change the shape of the mirror. So there was another laser which used to be used to to heat up the mirror in a way so that the shape of the mirror is maintained. So there are different kinds of things which were done to maintain the shape of the mirror, which is very important. Melting, of course, would not happen, but then if there are small deformities on the surface of the mirror, they would burst, and then they could create more serious deformities on the mirror, which would reduce the quality of resonance in the cavity, and reducing laser power. So all those things are also there. Okay, coming back to this match filtering method, that how would you detect a signal which is buried inside noise? See, this blue thing here is noise, and here you see this small red thing is the signal. So how do you detect it? So let's say that you have a very good theoretical model for this signal, but you don't know where it is. It could be here, it could be here, and so on. Then how do you detect this? So you take this model signal called a template, you place it here. Take the cross correlation with the data, plot here. Again, shift it, plot here. And that is what we will see here in an animation. Of course, there is nothing moving. It is like just to show that plot, place the template here and put the cross correlation here. So you see that when you do that, the cross correlation is low, but as soon as the signal matches the template, there is this peak. Since it is statistically significant, it is above the cross correlations caused by noise, you can claim a detection. Of course, it is far more complicated to actually claim a detection, but this is the basic idea. And in practice, what is done is that there are these different mass parameters. These are expressed in terms of in units of time and so on. There is a grid which is placed, and for each one of these mass pairs, let's say each point corresponds to a circle, corresponds to couple of two masses for this binary, and for that you create a model template and then search the whole data set with that, and they keep doing that. Actual parameter space dimension is more because there spins of the black holes also involved and things like that, but this is again a very basic idea. And of course, you cannot place them infinitely close. You have to choose how far you want to place to reasonably cover the space without losing many signals. So these are the considerations one has to do. Okay, so now the thing is that after all these things were developed for a long time, decades, but still there was no detection until recently. Why was it so? So the first generation LIGO detectors were started operating in the 1990s. I think they operated till 2005 or so, and the probability of detection there was only 2%. So what was the purpose of building that detector? It is to show, because building detectors require a huge amount of money. But then government would not pay you so much until you prove that, okay, this is a feasible technology. So initial LIGO showed that you can reach within 1 order of magnitude sensitivity. That is, the sensitivity was less by a factor of 10, but it could be reached with some uh, with that amount of smaller amount of money. And then it was basically done in a staggered manner. Then finally, when the funding agencies were convinced, they gave money for the full advanced LIGO detector, and then the sensitivity improved by a factor of 10, which means that the volume coverage improved by a factor of 1,000. And then this is the predicted detection rate, which is sort of what we are seeing in black hole cases, but not in neutron star, and that will require more time. So this is the kind of what it means. So this was the reach of initial LIGO, and the advanced LIGO has 10 times more sensitivity. So the volume coverage becomes 1,000 times more. So the probability also increases by a factor of 1,000 at least. Also the bandwidth is larger, so it becomes even more than 1,000. So there are several things which were done for advanced LIGO. Initial LIGO had a laser power of 12 watt. Advanced LIGO's design is 120 watts, even though right now, so far it is operating at 70 watts. Then there are many other changes here and there. So the mirror was increased from 10 kilogram to 40 kilogram and things like that. Anyway, these are some of the details. This is how the sensitivity improved, and this is again the important thing, that it takes very years to improve the sensitivity. There is no magic here. People have to work very hard to go from here to here to here. You see that these are long time scale to improve the sensitivity. Okay, there is a question: what is the meaning of volume coverage? Well, the probability of so suppose a signal is emitted nearby for a given mass. Let us fix the masses, and then if something happens nearby, then the chances of detection is more. If it happens very far away, then probably we are not going to detect because the signal will be too weak. So volume coverage means up to which distance in a given configuration, like the masses, the orientation, etc. If they are fixed, then up to which distance you can the detector can see. That number of course varies, but if you take one set of numbers, then there is something which will be like some horizon which will increase by factor of 10. That is what it meant by uh, the volume coverage. Okay. Do gravitational waves decay for large distances? Yeah, it goes down as we showed saw in the last class as 1 by r, like just like electromagnetic uh, field. So the energy drops as 1 by r square, like electromagnetic normal light. Yeah. So does the intensity vary as inverse square law? That is the question. Yes, the intensity varies as inverse square, and the amplitude varies as 1 by r. Okay. So this is after all this, then finally in 2015 September, gravitational waves were detected, and this is one of those simulations which were this kind of softwares were also used in this movie called Interstellar, where Kip Thorne was one of the uh, founder of the LIGO detector, primary proposer who got the Nobel Prize, was involved, and you might have seen these kind of things there. Okay, moving on. But this is a real simulation. It is not something to do with the movie. Okay, the next major discovery that happened was a of a binary neutron star merger, which is also called GW17017. That is, this was detected on 2017 August 17. This one was because black holes don't emit any other electromagnetic signal, but binary neutron star mergers do. This was observed by many other optical and meaning electromagnetic telescopes. Like it was a gamma ray burst was observed, then a kilonova was seen in the optical telescope. Then radio waves were observed weeks after the merger and so on. This here the localization with a network of detectors, which somebody was asking, played a crucial role. So what happens is that with only initially, okay, let us see. This was detected by Fermi. LIGO actually detected before, but then that came that actual thing became later because it takes some time to analyze. So this was the kind of overlapping area with these electromagnetic waves. With two LIGO detectors, this would be okay. Let me oops. With two LIGO detectors, um, this would be the area localization area. Okay, basically it is a ring on the sky, but these parts are not LIGO detectors are not sensitive to these parts, so you can rule out that nothing happened here. But you will see that with the addition of the third detector, Virgo detector, the localization accuracy improves much more. So now it is LIGO and Virgo. See, it became much smaller, and that is because even though Virgo did not have enough sensitivity to see it, but that no detection meant that it is not in certain areas. Now, using those localization, people located actually spotted the host galaxy, and that gave us the redshift and so on. So many detectors across the world observed this day and night, and then 3 Indian detectors, telescopes also participated in this activity. And you have to do it globally because, of course, you have to observe. You can observe with electromagnetic telescopes, mainly the optical and so on, only at night. Okay, so this is the very nice animation created by NASA of this video. You see that these two neutron stars are going around, then they merge with gravitational waves, and then a jet comes out, which hits the interstellar medium and creates afterglows. Yeah. Okay. So there is a question that why did other LIGO detector point in totally other direction? No, I mean there is the detectors are LIGO detectors cannot be pointed to any direction, right? I think I told you yesterday. They are omnidirectional. It is not like a telescope that which you can point to some direction. They are getting signals from every direction. But then, uh, if two detectors are receiving a signal, considering the time delay between those two signals, you can locate them on a certain ring on the sky, and that's what these detectors do. The Virgo detector also have full coverage, but then it was insensitive to the region where the actual actual event happened, which means that since it did not see the event, but it was sensitive to see, the event has to be in that region. That's how you localize it. So then there are these more some of the interesting signs that came out of it is one of this is this. This sound would be the sound of gravitational waves if you converted uh, played them in an audio detector because they are in the audio frequency band. Now, what happens here is that after the gravitational waves were detected, even the gamma ray detection happened within 2 seconds. So this basically means that, and they traveled about 40 megaparsec. That is 10 to the more than a few times 10 to the 15 seconds. But the difference was in only in 2 seconds, which means that the velocity of gravitational waves, speed of gravitational waves in vacuum, let's say, of course, I mean, there is no other way, and the speed of light in vacuum, they match to at least till 15th decimal place. Any variation can happen in 16th decimal place. So somebody was asking if there is an experimental verification, so that is what it is. However, you can never prove this because one could argue that no, maybe the these electromagnetic waves were emitted long time ago or later or something like that. So the speed could be different. So that is how science evolves, right? I mean, you keep doing experiments to see how long it sustains, and then um, when it is broken, then you know there is something wrong with the present theory, and then you create another modify the theory. Okay, there is a question that so the 2017 black hole collision was within the volume range of Livingston. Yes, yes, of course. Otherwise, we would not see it. And it was not black hole. It was actually neutron star collision. The range for neutron star is smaller. For black hole, the volume reach is larger because black holes are bigger than neutron stars, and so they emit more gravitational waves. The amplitude is more. The frequency is less, though. Okay. The other thing that we learned, so this was one science this thing that that gravitational waves travel at the speed of light. If they did not, then probably we need to uh, uh, have modifications to general theory of relativity. This is people will keep doing this test until it breaks, and maybe it will never be broken. Now, the other thing we learned is that how do you get these heavy elements in nature? You can always take smaller atoms and sort of fuse them, like what happens in stars, that you can take uh, different uh, you say let's say hydrogen, you take hydrogen, form a higher atomic number, let's say carbon, oxygen, all those things you can form. The problem that happens is that after you reach iron, then you cannot fuse things anymore to create uh, higher elements because that will require energy. This is not going to emit any energy. In stars, these lighter atoms merge to create energy. So then where do you form these heavy elements like gold? And one of the theory was that they form in merging neutron stars. And the follow-up observations proved that these merging neutron stars actually create a large number of elements in the periodic table in very good quantities. A large fraction of it is created in the merging neutron star. Let's say uranium is almost entirely created in neutron stars, and so on. Okay. Other elements like silver, etc., are created partly in neutron star, could be partly in supernova, but supernova alone cannot explain the whole abundance. Okay, so then what else did we learn? The thing is that first thing is that this theory that when two binary neutron stars go around and then finally merge can create a gamma ray burst was proposed, but then this is the first time it was proved that this is really a right theory. Okay, another question is that this is a bit stupid, but okay, are there elements on Earth that are from? Yes, the elements on Earth, the gold that we wear, were created in such collisions, and that is something sort of maybe philosophically interesting to think about, that all the things we are made of elements which were created during, okay, most of the elements are light, but the heavy elements that our body has, or at least we wear, let's say that ornaments, the computers we are using, etc., those things were actually those elements came from neutron star merger, supernova, etc. Okay, moving forward, we also got, because the host galaxy for this neutron star merger could be located, we got the exact redshift pretty accurately. We also got the distance to that galaxy from the gravitational wave signals, because from the phase information of the gravitational wave signal, we can estimate the masses pretty accurately, and from the masses and the distance, we can get the amplitude pretty well. Now, by comparing the amplitude that we have detected in the detector, we could say how far away that source is. So this way, we get the distance and redshift both, which gives us a measurement of the Hubble constant. You may be knowing that that there are two different measurements of Hubble constant, very precise. One is this green one, which is from CMB observations, and then there is this saffron type one, which is from supernova observations. They are both precise, but they don't match. So one of them has to be wrong. Now, with gravitational waves, we get an independent measurement. Now, the error bar at this point is very large, but as we get more and more detections, this error bar is going to shrink, and hopefully one day we'll be able to distinguish between these to see which one is correct, or maybe both are wrong. Okay. Another question: what is the time scale of that neutron star merging? I mean, the neutron star merges for very long time. I mean, it takes probably millions of years, but or at least hundreds of thousands of years. But the time scale within the detector is of the order of few seconds. So this one maybe tens of seconds. Neutron star signals are longer than black hole signals. So this is how it goes. Okay, so yes, somebody is asking that does this mean that the neutron star collisions are standard candles? Yes, they can be treated as standard candles. They are the new standard candles. Unfortunately, we have only detected one which could be followed up with electromagnetic telescopes. But hopefully, with the next generation, in the future detections, meaning updated detectors, we will get more. So here is the current status. So we have detected several sources. I think there are 90 of them here plotted here of various masses and sizes. These ones are the ones which were already detected by electromagnetic astronomy. You can see the populations are quite different. For each one of the detections, we have three because they are binary mergers. So you know the initial masses and this is the final mass. This is how they are plotted. Okay, I'm almost near the end of this. So now with all this, we are basically at the beginning of gravitational wave astronomy, and we have only detected a set of mergers, binary mergers in a given frequency band. There is a very long way to go, and basically we have to build a network of detectors so that we can follow up these sources more efficiently with electromagnetic telescopes, so that we can get, let's say, several signs. I will mention it in the end. We have to improve the sensitivities of the instruments and enter the next generation. So LIGO 1, the first generation detectors did not detect anything, but it was a technology demonstration. The advanced detector, that is the second generation detectors, detected, and then there will be the third generation detector, which will do astronomy much better. And they will, so there are plans for that, which I will show in the next presentation. So we have to build instruments at different frequencies. We have to build space-based detectors, because if you want to detect, for example, supermassive black holes, we have to go to space. The seismic noise on the Earth would not allow us to go beyond lower than few hundred hertz, few hertz. And most important for in the Indian perspective is in LIGO India. So that's also I will cover in the next lecture. So what are we going to do with this? So we have to see whether Einstein's general theory of relativity is correct, or if there is a limit where it breaks down. It is like probing, challenging, how science progresses. That you challenge Newton's laws and then you get, let's say, well, Newton's laws of motion you challenge, and then you get Einstein's theory of relativity, and that gives you also the ability to convert to get nuclear energy, which you can use, for very good or bad. Now, then there are so we want to also see the space-time geometry near the black holes. Is there an event horizon? Well, event horizon telescope does give one picture, but there are other ways to test them, uh, more sharper tests. How exactly is the universe expanding? Was there a cosmological inflation? This may take very long time to detect, and so on. So there are many different questions which are listed in something called the GWIC roadmap, that is Gravitational Wave International Council roadmap. There are many science questions which are listed. You can, if you are interested, you can see what are the science questions which will be answered. Okay, I'll stop here. Let's see, there is a question that, okay, please explain the graphs on slide number 50 once again. This one. So this one is basically the measurement of Hubble constant. X-axis is Hubble constant, Y-axis is basically what is called the posterior, the probability. These ones, this green and this whatever orangish colored ones, are measurements of the Hubble constant from CMB and supernova. So CMB measurement is below 70 kilometer per second per megaparsec. That is around 68, and the supernova one is around 73 or so. So that is here, and these blue ones are showing the error from gravitational wave measurement. The error bar is very large, but with multiple, as we detect more and more, this error bar is going to shrink because you can stack those observations, and then at some point you may be able to distinguish between these bands. And what is plotted here is also the similar thing, but this is the evolution of Hubble constant measurement error. So the error bars were very large in early 2000. They became smaller, and now in 2000, let's say we are kind of here. That I don't think there is any update to the plot. We can check. The error bars have now become much smaller, and then there is this new one which is from gravitational. When this becomes small, then we'll be able to distinguish between these blue ones, which are basically from CMB, the supernova and so on, and the red one, which is from CMB. See, both have very small error bars, but then they are different. So with the purple one shrinking, we'll get an independent view of which one may be correct. Okay, there is another question that can he suggest an undergraduate level paper for gravitational waves, which I found to be very important and interesting. It could be experimental theoretical paper. Yeah, so gravitational waves, there is a review by Satyaprakash and Schutz. You can see that that's a very extensive review. It's probably beyond undergraduate level. Now the thing is that okay, I did not want to do a self advertisement, but I have me and Sanjit Dhurandhar have written a book on gravitational general relativity and gravitational waves. That book is the international edition is pretty expensive. So if you have if your institute has subscription, you can probably download. But we are also trying to see if an Indian edition could be brought out soon. Then the question is that what could be the reason for the difference between the CMB and gravitational waves posterior? So how to concept it? If I knew it, this is one of the most important questions right now. People don't know what is the reason. This is the hot topic of research. Yeah. Okay. If there are no other questions, okay. Somebody actually raised hand. I think Prasad Basu here. If you raise your hand, then I can unmute you. Okay, I don't see any hand up here on Zoom. So okay, there is. Okay. Yeah, go ahead.
Achha. So you talked about the as a so one of the major goal of this gravitational wave discovery is to do the precision astronomy with gravitational wave, right?
Right.
So the question that they like to answer is like, what is the beyond Einstein modified theory of gravity
Yes.
or naked singularity existed in like this?
Yeah, I mean, it is just not just precision. It could be also paradigm shifts like this. That maybe Einstein's theory is not right. There will be modifications needed, and so on.
So no. So my point is that if we can do precision astronomy, then we would be able to answer these questions, right?
Both are important, right? I mean, precision astronomy is on one hand like measurement of Hubble constant, but on the other hand, you also can do if we could see the ring down signal of black holes very precisely, then we may be able to say whether it is consistent with no-hair theorem or not.
So my question is, with the present sensitivity of these detectors, is it possible to do such kind of study, or we need to improve? If we need to improve, so how much we need to?
Oh yes. I will cover this in the next lecture. Is about that. But the thing is that, but it will be more on the detector side. But yeah, so the question is that you can. It is a smooth process. It is not like a sharp thing, right? So, for example, that velocity of see this one, that which showed that the velocity of gravitational waves and velocity of light are consistent to like 10 to the minus 15 or more or better, already is a test of the GR. Because now if this kind of test happen, then if there is a massive gravity, the graviton mass is constrained already in for those theories. So these are pretty good constants. But then on the other hand, like one could argue that well, we don't know exactly what happens in the gamma ray bursts and this thing. So this is going to evolve with time. But these kind of things we can do. But the thing is that if you are but then going beyond, like testing nowhere theorem and also testing whether mainly nowhere theorem, let's say, those things in my opinion will be possible only with the next generation detectors. Right now things it will be very difficult.
I mean, Lisa or LIGO, which is the most potent detector or possible for whom it is more possible to do it? Lisa or LIGO?
They are going to probe different things. Lisa is going to see the supermassive black holes. Of course, you could argue that the general theory of relativity is independent of it is supermassive or not. And then LISA is also going to see the extreme mass ratio in spirals, where, like, there is a supermassive black hole, and then by looking at the orbit, you may be able to map the space-time in that region very well. But then it is around supermassive black holes. LIGO may be able to see for stellar mass black holes what is the ring down signal. So these two are different things, but yeah, LISA would probably have slightly better chance of probing general theory of relativity. That is possible.
Okay, thank you.
There is another hand up, and there are two more questions. One is that, is the gravitational wave produced by the merging of two neutron stars act like a carrier wave? Because the EM waves are also ejected. No, they are not carrier wave like EM. They are just two separate waves. It could be like, when you burst a cracker, there is light and there is sound, but it is not that light is carrying the sound and things like that. Then there is one more question, is that, are we building new detectors for BNS? Well, we are building new detectors. Hopefully they will detect a lot of BNS. Okay, there is a hand up. A Vasan.
Yes, sir. Sir, am I audible?
Yes, I can hear you. Little broken, but then yes, it's fine. You can try.
Sir, what is meant by gravitational multi-messaging astronomy? What it signifies?
No, it is not very clear. Can you say a little more, or you can type in the chat box. Okay, I think this is the last question. Then we'll stop. Okay, I believe you are typing the question. Yeah, okay. The gravitational multi-messenger astronomy means what? Means that when you look at this signal, let's say from 17 it was observed in multiple wavelengths. Okay, in electromagnetic waves and also the gravitational wave signal. So each one of them gave us different information about the same event. So it is like, trying to find some blind people trying to understand how an elephant looks. So this is the kind of thing. So this is why it is called multi-messenger astronomy. So there are different messengers. Messages are coming in different wavelengths, let's say. Okay, I think we'll stop here. Okay, and you can ask more questions tomorrow. Yeah, bye.